We're gonna have Anna now giving the last talk for the day.
Great, thank you, Max. Thank you for inviting me. I'm really excited to be here. I'm Ana-Andreea. Stoica. I'm a research group leader at the Max Planck Institute for Intelligent Systems in Tübingen, in Germany, just like Celeste. So today I'm going to give a tutorial on diagnosing algorithmic inequality in social networks. And mostly this tutorial is designed to show how and why network structures contribute to inequality within societal distributions of resources. And we'll mostly focus on resources that are distributed through algorithms, such as information campaign, recommendations, and so on. So first of all, I want to start with some empirical examples of, does this work? This worked earlier.
You just may need to click on the screen. You may need to click on the slide. Yeah.
Oh, great. Thank you. With some empirical research showing that network structures correlate and embed inequality as measured through socioeconomic factors. And empirical data is particularly important because it gives us a glimpse into the structures created, for example, through showing that bigger cities are more densely connected and have higher connectivity between people that reside in them, but probability of making connections with your friends of friends is kind of independent of the city size. Other studies show, for example, Smith and Clark in 2014, that decreased communication to and from a certain area correlates with poverty. And a lot of these studies are actually here. This is okay. A lot of these studies in the past have focused on looking at cell tower data and figuring out networks of people based on the communication between them. There's a sense that your position in the network matters, and the number of connections that you have are a proxy for the kind of opportunities or access to resources or new technologies that you may see. And one way to formalize it was...
by communication edges, we're talking about like social networks here,
yes,
mobile phones, or...
We're mostly talking about social networks. So a communication means that people have some sort of social connection between them, and that is one way in which you might create a network of people together with their social relationships.
On like Facebook, Twitter, or whatever.
Yeah. And these are kind of like real life connections based on like mobile telecommunication data, but we're going to go into online networks from here on as well. Yeah. So your position in the network matters. One way to formalize this was in the early 2000s, from thinking about what is your social capital and how the number of connections matters a lot in terms of what you can access. And Putnam defined two types of structures that are highly informative of how we think about network models these days as well, which are like bonding structures and bridging structures. Bonding structures mean that if you think about different groups, for example, demographic groups, interest, religious groups, and so on, people derive more utility from focusing inwards, connecting with people who are similar to them, than connecting with people who are different from them. And maybe that similarity is subjective, of course, on the kind of groups that we're forming. And I know Lily mentioned a lot on what does it mean to be similar is a highly subjective and personalized experience. Bridging structures means more that you're connecting with people who are different from you. And that has a lot of applications in voting, in forming election committees, in local city councils, and so on, in school councils, thinking about what is a representative group of people who can come together and make decisions that are representative of the general population that they think about. These kinds of structures have been shown in empirical studies to correlate a lot with inequality, particularly with economic inequality.
Sorry, just to make sure I follow.
Yeah.
The idea is that everybody's part of these different networks, and we think of some of our types of interactions are bonding type, and some of them are bridging type.
Exactly.
But like I have my whatever Twitter connections, I have my mobile phone communication.
Yeah. So one example of a bridging connection would be, of a bonding connection would be to see that minority groups are shown anecdotally and empirically to have a strong social safety net by connecting more with each other. Diversity and inclusion initiatives are a type of bonding structure, whereas a bridging structure, you can think about it as like a electoral committee or a committee among your neighborhoods of bridging between different types of people who are trying to make decisions about local transportation needs.
But the idea is that society consists of like multiple layers of networks that have different.
Yeah. Or like these kind of structures are present in society in various different levels. So figuring out how they interact with the way we access different kinds of opportunities is important. Yeah. There was a question in the back as well.
I was just wondering how these bonding and bridging groups were measured and determined.
Yes. Well, I'm going to show you right now. here's a study that is looking precisely at that. In 2019, Pinocchio et al. Finds that poverty correlates with bridging communities, whereas wealth correlates with bonding communities. So I'll go into details for a minute on that. They take a network of people and they use the mobile cell towers in Cote d'Ivoire to measure the amount of communication between different areas. So each node is an area and an edge is weighted based on how much it communicates with other areas. They are weighted by these areas, and what they find is that you can think about different measures that are network measures as bonding versus bridging measures. For example, a bridging measure is between a centrality, thinking about how far can you get from one area to another. I don't go into the definitions of that. And a bonding area may mean like a local clustering coefficient of like how likely are you to be friends with your friends of friends. So what they find is that poor areas were much more bridging outwards towards other areas, where richer areas which much more oriented inwards. In a sense, you can think of it as a measure of almost segregation. I hope that answers the question as well. There's a lot of studies, even a lot more recent ones. There's a very recent study by Cherry et al. That thinks about homophily, the relationship between homophily and equality. And they have this data from 70 million people on Facebook and their social connection, together with they correlated with a bunch of other measures, such as the social economic status from survey data and so on. And what they find is that the share of high economic status friends among individuals with low socioeconomic status is the highest predictor, one of the strongest predictors of upward mobility that they identify today. So your likelihood to connect with people who are better off in terms of income and wealth is this bigger predictor to say how likely you are to move upwardly as well. This is, for example, the map that they find, in which the colors find like how likely are you to connect with people who are more in a higher socioeconomic status. Red means that you mostly connect with people in your own socioeconomic status. This is the image taken from the point of view of low socioeconomic status people. So you can see that a lot of the poorer areas also, well, it kind of depends, but it correlates a lot with the mobility data that they have. So people who are more connected with people from the same socioeconomic status, a lower one, are less likely to move upwards. And this is a kind of correlation that they find, in which the likelihood of you to connect with higher socioeconomic status people correlates positively with your probability to have better mobility in an economic sense as well. Are there questions so far? Okay, good. In a different study, this is an older study from the Maggi and Garrett, they show that homophily, this tendency of people to connect with people who are similar to them, in a sense of bonding structure, leads to increasing intergroup inequality when in the internet adoption rate in the US. So here, when we think about inequality, we don't think about the socioeconomic inequality that we just mentioned, but inequality in your access to a new technology, which was at the time internet in the early 2000s. So they take this survey that has a bunch of information in it, from demographics, African American and white respondents, to education levels, income, together with the network size of different people. And they create networks in which they simulate the various levels of homophily among these different features on race, education, and income. And they simulate the diffusion, and they compare it with the actual adoption of the internet, but they simulate the diffusion of who is likely to adopt internet if they hear it from their friends through a diffusion model. It's a threshold model. And what they find is that the more homophilic you are, the more likely you are to have like a cluster network, which means you're going, higher homophily means higher age, so you're going to the right, the less likely or the longer it would take you to adopt internet. So this is the proportion of people who adopt the internet, and this is time. And the more homophilic these networks are, the longer it would take for you to actually like adopt this new technology, which in a sense makes sense based on the structures that you create, since you have a much more highly clustered network. They find a bunch of other things too, that homophily doesn't affect people in the same way. So if you actually think about if you look at the odds ratio, the proportion of the highest income over lowest income for people who adopt the internet they say that they see that homophily has an interesting effect here as well. So if you look at a more homophilic society, based on income classes, and you compare who is the proportion of people who adopt internet, it is going to advantage the people who are on higher income bracket. So the proportion of people of high income over low income class, this odds ratio, it's much higher for a more homophilic network than for a less homophilic network, which means that not everyone gets affected in the same way. The people who are more advantaged to begin with are more likely to, in this case, adopt a new technology. They seem, yeah.
I don't really want to be that economist, but
Yeah.
in all of these stories, you can think of a lot of confounders, right? That's when correlations might arise for all kinds of reasons.
Oh, for sure. This is simply a correlation that they find. And I'm sure that there's many reasons to it. The kind of analysis that they do looks like this. So yeah. But there are many studies that kind of find this, and the big question here is like, are these studies, relevant for us? Can they inform the models that can explain a little bit of these results that we see, and can help us design studies in which we can find a better explanation or an actual explanation for this? They do find a consistent effect for various types of features. So they find consistently that you're more likely to adopt this internet basically if you are more advantaged in terms of high income, high education as well. So it's not that everyone gets affected in the same way, but it increases among the most prosperous, particularly when you have homophily.
Yeah, sorry. So feel free to just, I know this is not your paper, so, but is this sort of empirical results or are these simulation results?
So these are
calibrated to that?
Yeah, these are two types of results. This one right here is a simulation result. They do compare it with the real data that they see from survey, and they see it's quite related, but in the survey they can't really vary the level of homophily, so they see it at a fixed point. Yeah. Good. Sorry. But my point here is that there are the structures that correlate with the kind of opportunities or that you may access to your leveling of net in your society in terms of your socioeconomic prospects. And it's important to think about how your position in the network may affect exactly what we were talking about. A lot of these studies were done in real networks of people where opportunities are diffused, let's say, in society through different means, but a lot of them now happen through the means of algorithms on online networks. And even there, the kind of networks we see are highly skewed and it's very important to understand the structures that are created there as well. So if you look at online networks, studies from, again, the early 2000s show that social networks are also highly unequal in terms of the number of connections they have, that oftentimes the degree distribution of people follows a power law in which very few people are very well connected, they have a lot of social capital, and most people are very well connected or lurkers on the internet, which we see in a lot of the online data sets that we gather and see even now after, a few decades. Good. So the rest of the tutorial is going to be split into two parts. I'm going to talk about how do we use networks to diagnose when and how an algorithm may amplify bias between different groups, whereas they're demographic groups or interest groups that we care about to make sure they don't have differentiated access to different opportunities that algorithms give. I'm going to focus on a set of unsupervised graph problems in which algorithms are developed to give particular resources and try to think about a theoretical formulation for capturing distributional inequality. And we're going to leverage network models to recreate this root cause of bias or inequality we see in networks and understand how that gets affected by algorithms on networks. In the second part, I'm going to have, as much as time permits, talk a little bit about using networks to test algorithms. We've talked a lot about randomized controlled trials, so I'll touch a little bit on the problem of interference in networks. Great, so let's start with the first part. When we think about an algorithm that gets deployed on a network, we think about, well, what do people gain or benefit from that algorithm? It may be that they gain new connections, maybe they got a piece of information. There's many ways in which you gain something or you benefited something from the connections that were either there or were newly formed as part of this algorithm. And I want to start with an example of social recommendations. This is a data set that was collected in our lab a few years ago. It's a social network collected from Instagram where people are the nodes, and there's a connection whenever you liked or commented on each other's photo. It's a large data set of about 500,000 people, and there's two groups that we see in them, men and women, in slightly different proportions. This data set was interesting because it was collected at a time when Instagram did not have the who to follow feature. So the connections that you see on this data set are in a sense organic. They're not recommended by an algorithm because there was no such algorithm to recommend them at the time. It was about in 2013. What you see here is the degree distribution, and I want you to look only at the blue nodes. I'm going to explain the other colors in a little bit. But the blue nodes represent the proportions of women among those with degree at least what's on the x-axis.
5,000 is a very high degree back then.
Very high degree. Yeah, I mean, this is the subset of the network, but at the time, like, yeah, that was a super highly central person. So what you see in this subset of the network is that the proportion of one of the groups, in this case, the women, as you look at people with higher and higher degrees, slowly goes to 0, which means nothing about Instagram or these particular two groups per se. It just means like, well, this is how the subset of the data looks like. Maybe it's the way the data was collected and so on. But it's not that on average, the two groups have very different degree. I'm going to show you that, is that you see this difference for people who have very, very high degree. The circles you see around are just the size of the population at that degree class. So there's a lot of everyone at the beginning has degree at least 1, and as you move with people of very high degree, there's very few people. The dashed line here is just the percentage of women in the general population, about 54%. Now, what happens when you apply different social recommendation algorithms to?
Sorry, could every group have a lower share than the overall? If the share of women is lower in every subgroup?
Oh, not lower. So it's kind of like the same here, and then lower just on this side and this side.
But shouldn't that sum up to the whole thing?
That times all should sum up to.
So only this is cumulative. So on the y-axis is the percentage of women among those with degree at least X.
Oh, I see.
So here it should be exactly at X, the dashed line, and then after that, it's how the cumulative data looks like.
I see, okay.
Degree means the number of connections that you have. And in this data set, it means it's an interaction graph. So if I liked or commented on someone's photo, that's a connection that we have. Okay.
So it's a regression function, basically.
Yeah. Okay. So because this data set had these connections, but prior to recommendation algorithms being implemented on it, or who to follow feature, we tried a couple of them. We tried the most common recommendations that suggest you a new person to connect to. And we looked at we looked at a bunch, but I'm showing you a couple of them. One of them is based on a Damekadar index, which basically tells me based on the number of connections, common connections that I have with someone, I have a higher probability of connecting with them through some function that processes our number of common neighbors. And through a random walk of length 2 by just saying, if I started someone, do a random walk of length 2 and connect with that person. So everyone gets a new number of connections. And we wanted to see, well, who got recommended to be connected with after you try out these two options. In green and in red, you see the number of recommendations that people got after these were simulated in our network. And what you see here is, again, the percentage of women among those with degree at least X. Not only it again goes to 0, but you see that it goes to 0 in a sense much faster. This is not a speed version, but you see that there's a gap here in which the percentage of women just like drops to 0 at a pretty high rate as you move with people who are more and more recommended. So there's a sense.
Somehow women are less friends of friends.
Yeah, it's weird, but if you, intuitively, in a sense, what actually explained this, and I'm going to show you in a little bit, is that they connect more with everyone, so they're more likely to be connected afterwards. They're less. I will explain how that works in a bit, but they're less likely to be recommended. And one explanation for it is, well, maybe they just have fewer connections, but there's more that explains that. It's also the way they connect with each other and with the other group, in this case, the man. Let me show you a short illustration of what this graph actually means. So if you look at the blue dot here, this is just in the original graph. Oops. Okay, we're back. This blue dot here that basically tells you that in the original graph, if you look at people with degree at least 10, with at least 10 number of connections, you have 52% men and 48% women. If you look at the green dot here, this is this part here, it shows you that, well, the number of people among people who got recommended at least 10 times, you have 64% men and 36% women. And that's one way to interpret how these curves move forward. So there's a sense that this kind of algorithms kind of amplify the difference in the number of connections that people are able to gain, not necessarily on average, but at this distribution level among people who are likely to be very well connected. Good. So this is one example in which I'm showing you that, there's a sense that algorithms may amplify a bias that pre-exists. It didn't really create something, but it amplified the difference in social capital between the two groups we saw in our network, in this case, men and women. And there are many different other types of graph problems in which we're interested in analyzing this. This was one kind of benefit where you get new connections through recommendation algorithms.
It's kind of a rich get richer type thing.
Exactly.
Where if you already have more connections, you're more likely to be recommended again.
Yeah, exactly. And because it's such a skewed distribution, that rich get richer effect is so prominent that it's going to be picked up by recommendation algorithms and actually made much worse. There are other types of benefits that you get in this class of unsupervised graph problems, which are maybe you're exposed to an information campaign that gets distributed through your network. Maybe you're targeted for assistance, for help, for new products or new groups that you should join. Or maybe you receive exposure by showing up in search results based on how relevant you are to a search. Yes.
So how much of these bias is actually driven by these extreme outliers, which happen to be men? I mean, perhaps we shouldn't care that much if Cristiano Ronaldo gets recommended a lot. It's fine as soon as the average man and the average woman actually gets recommended equally.
Yeah. That's a good question. I mean, it is in a sense important to not completely exclude the outliers because they drive a big effect because they're so well connected, but that means that we can't really imagine a world without them because they are in competition with other people. So if Cristiano Ronaldo takes away the recommendations of many other people because he exists in the network, then we should redesign, in a sense, the algorithm to say, okay, you got recommended a lot, maybe we should look at other people. But without doing that, you have to take it into account because it's competing with the other people who have much lower number of connections. Yeah. So there are many different benefits that you may get from different types of algorithms, and each of the examples that I'm getting here is defined through a different unsupervised learning graph problem. For example, the problem of social recommendations, information diffusion campaigns, clustering, and ranking problems. So we may ask, is this a problem between these different groups of people that we see in society in all of these kind of problems? Do we see this a lot? We saw it in the case of social recommendations. Do we see it in a lot of other cases? I want to give a very short example to show you that, yes, this is a prominent problem. We see it in a lot of recent studies that focus on a lot of these applications. For example, in the case of information diffusion, we saw it on this empirical / simulation side that internet adoption rates increase among the most prosperous in the presence of homophily. There's other modeling problems such as Okafor from 2022 showing that job referrals are likely to favor those who are already in very good positions in the network, particularly majority groups or people who are very prosperous from an economic point of view. On the CSL and algorithmic side, this is defined as the social influence maximization problem, in which you're trying to design algorithms that select a few people in an optimal way that will diffuse information and rely on their connections to spread a message to as many people as possible. And what they show is that if you just rely on, let's say, however you design your algorithm on a greedy measure, on a centrality measure, you're going to leave out minority groups out of this information loop. So if you're trying to diffuse a message and you don't think about communities, you're going to end up with underrepresenting minorities or leaving a minority group completely out of the information loop. And these are examples of recent studies that show that. On the clustering side, applications that may affect different groups differently are that of facility location, in which Jung et al. In 2019 showed that clustering can be highly beneficial to very clustered and economically prosperous groups, but not so much to others. So if you're thinking about where should I put buses based on how people group together in a geographical network, you might have groups of people that are more that are much worse connected, that will have to travel much more to the bus station or will have much fewer bus stations in their area than others who are already doing pretty well because they're in an urban area with much more better means of transportation. And finally, on the ranking side, there's a lot of recent empirical.
Sorry, just to summarize for myself. It's basically in both of these is like a tension between trying to maximize like how many nodes I reach within a short number of connections versus reaching those at the margin of the network.
Yeah, that's an example of that precisely. Or if you think about
also the influence thing.
Similar in nature, but here I think about like an actual like how much do I have to travel from where I live to a bus? Maybe I have also 2 bus stations that are close to me, but they're actually really much farther away than someone who lives in a highly prosperous neighborhood with a lot of other opportunities to travel. And finally, in ranking algorithms, for example, in search, there's a couple of recent studies showing that there's this kind of bias in exposure among different groups as well. And I want to show you an example of that. Search has been, example of search algorithms are PageRank and hits. PageRank is currently used on Google, as you all know. And there's a sense that minority groups get pushed down in the search results, although they should be as relevant and be as visible as others. There are 2 studies that show that. I'm going to show one of them. Lasciano and Amodio show that if you show the word person on Google search among different countries, and then you collect the search results, the images that show up, they are quite gendered, and the percentage of for example, men in Google image search results correlates positively with the gender inequality index measured somehow in the countries in which you are correlating it with. You may say, okay, this is something that I see in search. Does it influence me a lot? Does it matter whether I see it on the 5th rank or 1st rank? Anecdotally, it does, but also they show that it does in practice. So what they do with these search results, they run a human study and they say, let me show you these search results and then ask you different questions about who I should hire for some position. So they show you different profiles of men and women who are quite similar, and they ask you, should I hire this person or this person for a particular job, random job? And what they show is that people who see biased search results prior to making the decision of hiring give much more biased opinions of who should get hired than those who don't see these results.
Sorry, could you explain it? Oh, sorry.
Yeah.
Oh,
Sure.
no, you.
Could you explain again that result? So
Yes,
they
yes.
showed them images immediately after they asked them.
Yeah. So they show them images of search results.
Okay.
For example, person, this is what your search results should look like. Something else, this is what your search results look like. And they show them more biased results. Let's say you search for person and I show you 99%, I don't know, men versus women. And then right after that, in the same setup, they say, okay, now here are profiles of candidates for a job candidate. Who do you think should be hired? There's more details involved in the study, but this is the abstract version of it. And they see that, well, the people who are consistently show more biased result in the search are making more biased job referrals or job predictions in the candidates that they see as well.
Thank you very much.
Yeah.
And
Yes.
and in this case, sort of who the gender mix that they got shown was randomized, that the subjects of this got shown was randomized.
The
So
gender-
it's not that like I see the gender mix of the search results in my country, it's that. sort of
Yeah, they
it's
randomize it,
randomized.
yeah, exactly, so they randomize the gender mix and they see an effect of that, yeah, exactly. Great. There's another recent study that I think is about that we're gonna go in a little bit, but the main point is that your position in the search result matter. There's a sense that, well, if you get pushed down in a way that's not really relevant for where you should be, that actually has an effect. And we care to think about why does this happen? When does inequality between different groups that we might care about gets mirrored or even amplified by the algorithms we use on these social networks? So these are all different problems with different, the challenging part is that they're all unsupervised in a way, and then you don't really know what the ground truth is, but you want a way to evaluate their effect on different groups. And this kind of, I want to show you a brief way of thinking for how do we evaluate the output of such an algorithm based on the gain that you might get from the algorithms that we see. So we can think about, a gain function that models one, in a sense, social capital or benefit after an algorithm A is applied. And let me show you an example of that. We can write it in a close
So this is like an endogenous evolution of the network that's mediated by the algorithm.
Yeah, basically. And for example, if you have social recommendations, your gain is just the number of new connections that you may have. If you have information diffusion, your gain is the probability of getting the information that gets diffused. In clustering, maybe it's your number of connections that you preserve in the cluster, or it could be also some distance to the cluster center. And in ranking, it just may be your ranking score overall. There's a way to write it in a unified formulation in terms of the probability of connecting with, of gaining something out of the algorithm itself. But this is very, sorry, let me skip that. This is very helpful because it allows us to think about the more general theoretical framework for thinking about inequality among different groups regarding what do they gain in this gain function. So in this case in which we have all these unsupervised learning problems, we want to think about, is there an equivalent way to think about, are we fair to the groups that we have in our network, whether they may be demographic groups, interest groups, or minority groups that we care to make sure they don't get a much lower benefit than they should have. One way to think about is to just, well, let's evaluate our gain on average, among two different groups. And this is similar to what maybe some of you have seen in fairness in machine learning, in a supervised case, to say that, oh, my gain is independent of the group membership. Whatever group I'm in, I should have on average the same gain. The challenge is that, well, there's many definitions in supervised learning. In that case, what I basically do is I have a decision maker who selects a number of people who will receive a positive outcome, and I know the ground truth. So I can compare whether the ground truth is really what I have after my algorithm is applied. We don't really have a ground truth here. Whether I have a social recommendation, I don't know whether you would have made that connection yourself or whether this algorithm, actually helped you, you wouldn't have made it. There is nothing to define as ground truth. So this can be helpful on measuring on average, but I want to propose something a little bit more is that we look at the actual distribution of gain among people in different groups. So what is my probability of getting a particular gain if I am in one group versus another group? And the reason for which this matters is that if we come back to this Instagram data set, and I look at the degree distribution that I have in my original graph, if I look on average, it really doesn't tell me much. The average degree of people, it's mostly the same. It's not going to differ that much if I add these recommendations. The difference is if I look at among people with very, very high degree, that's where I see that, well, the proportion of one group went to 0. And it matters that it went to 0 among those because those are highly, highly influential people. So if they don't have an ability to increase their social capital, that becomes a problem as well. Yes.
So I think I'm completely with what you're doing, is just connected to what we had earlier, right? In the list talk. In a way, you're shifting from like talking about something like fairness, as in like you hit some like latent target, or you treat similar units similarly, towards just thinking what's the causal impact on the outcome distribution of the affected, right? which I'm very much in favor of. It's kind of a conceptually different thing from either the fairness or supervised learning target.
Exactly. And I argue that we have to do that because if you're constrained by just looking at, on average, looking at what you are, or evaluating things, what's the benefit among different groups, then you're a bit stuck. You don't really know what to do and how to redesign things. And maybe you design things that on average are fine, but at the tail distribution are terrible. And this matters a lot because if you think about who diffuses a lot of information in the network, it's going to start from people who are highly central, as an example. Okay. So we have the sense that there's this, in the case of social recommendations, we saw this gap between, we have a network, there's some inequality in the degree distribution. Somehow things seem to have gotten worse if we add social recommendation. And we have a way to think about the outcome, but we don't really have a way to, so far, to prove it or think about it and understand what are the mechanisms that lead to that. And
so
then
it's the random walk effect. If you have the Markov transition matrix and you square it, you kind of basically square the eigenvalues.
Yeah.
In some sense.
Exactly. Yeah, that's one way to think about it.
That's kind of where the green dots are coming from.
Yes. That's where the red dots are coming from. The random walk.
Oh yeah.
Yeah. Exactly. So in this next part, I want to think about what kind of network models might be helpful for us to understand these effects, to create some explanation in which, some models may be helpful for us to recreate the root cause of inequality or bias among different groups that we saw, and to understand what's the impact of an algorithm on these groups moving forward. Let's see. So these empirical observations of bias or inequality have been very helpful to assess when an algorithm is biased among different groups. When do different groups have the same probability of receiving an outcome, for example, in classification, or when they don't. But the fairness literature, as maybe some of you know, has a lot of definitions and constraint-based optimization methods for debiasing such algorithms as well. But without a model that actually explains where does bias come from, and it is just difficult to know whether an algorithm mimics the bias that exists or it truly amplifies it. So, there is a set of causal reasoning or counterfactual reasoning papers that think about the causal relationships between parameters and variables. On the one hand, they don't help measure the amplification of bias. So the role of this upcoming section on network models is to try to explain where inequality or bias originate and to predict a state of the world in the absence of an algorithm for us to be able to compare what would happen if an algorithm is actually applied on it. And I want to start with a model that's, it's quite nice, it's simple, it's very applicable in a lot of the settings that we talked about. It was proposed by Avin et al. In 2015, and it's basically preferential attachment with homophily. It's an organic way of forming connections between people in which the network evolves at each step. So the way they start is to say we have two groups, blue and red, and one of them is in minority, one of them is in majority. At each time step, a new node comes in and forms a new connection or a new set of connections by choosing someone with probability proportional to their degree. So this is a preferential attachment, meaning that the higher the degree you have, the more likely you are to receive new connection as the network evolves. This is the model that was proposed in one of the studies that I've mentioned, Barabas and Albert in 1999, when they were trying to explain why the internet looks like they have a very, very skewed power law degree distribution among the online networks that they observe. So the preferential attachment part is also called Barabas-Albert model. And this leads to a power law degree distribution. The third part of the model, which differs from this, is homophily. If people come from have different labels, then connection is only accepted with a certain probability, which leads to this, clustering effect. You're more likely to connect with people. If you're red, more likely to connect with red. If you're blue, more likely to connect with blue. What this paper shows is that, well, not only that you have a degree distribution that's a power law, like you have in preferential attachment, but now the power law among the two groups with homophily actually you have two power laws with two different coefficients that differ between them, and there's a gap between them. which means if you look at, this is the number of people with degree at least K. If you look at the number of people with degree at least K that are red over that are blue, this fraction will basically go to 0 as your degree increases. And this is one way in which we can see this. They call this, in a sense, a glass ceiling effect, because as you move towards people with very, very high degree or a high social capital, one of the groups essentially vanishes. It's unable to reach there as the network evolves. They did this a bunch of data sets. One of them that's cool, that's from DBLP, which is a website of computer science publications. And they say an author is connected with other authors if they are mentoring that author based on the number of the seniority and number of papers that they publish with them. And they have also about 500,000 people with two groups, men and women, women in minority here. And what they find is that, well, this model models the data pretty well, in the sense that, well, if you look at the percentage of women among those with higher and higher degree, except a couple of exceptions here that are very well connected, it basically slowly goes to 0. And then they fit the two power laws with some other statistical tests to show that it's two different power law distributions. They relate this model and this degree distribution with different measures of inequality between the two groups. One of them is just look on average, the degree, delta is the degree, the average degree for the two groups, which may differ a little bit in practice, as we saw on Instagram. Same with DBLP, doesn't really differ much. The other two relate more to the distribution of this power law that we saw. One of them being just like the proportion of minority over majority among those with high degree. And the second moment's another version of that that's stronger. And what's interesting about this model is that it has very few ingredients, but each of them is necessary and sufficient to get this measure of inequalities that we see that they evaluate for. So if you have these 3 ingredients, you get all 3 of them. If you don't have a minority-majority split, you basically have just like preferential attachment, and the two groups are equal, and maybe there's homophily, so maybe they're clustered, but they're in equal numbers, then you don't get anything. The distribution is exactly the same. You don't get any inequality in their degree distribution whatsoever. If you don't have homophily, so if you have two groups, there's preferential attachment, but they connect equally to everyone. Maybe they will have a different degree on average, but that's because of their size difference. The actual distribution is the same. And if you don't have, if they actually connect differently than preferential attachment, then it depends how they connect it. So we're not going to go into that. But the main point I want to make is to come back and use this model to understand why social recommendations behaved in the way that we saw on Instagram. So if you take this model in which you know you have 2 degree distributions that are different, and you add to it a recommendation based on a random walk of length 2, then you can you basically get an organic growth model without any recommendations and a recommendation model in which you either connect through this preferential attachment that I showed before, or you get a connection through a random walk of length 2. What you get from this is that, well, if you add these recommendations, you still get a degree distribution with 2 different power laws among the 2 communities, but you can show that they actually grow further apart. And that's what I mean by what we mentioned before in this data set, an algorithmic amplification of bias, that you started with a network in which there was a difference in the degree distribution between the 2 communities, and now that difference got even higher at the distributional level. If you looked at just the average, that difference really doesn't get that much, but that's where when you make this analysis and you look at the distribution of degrees, that's where you get to see this difference, and we can prove it.
And presumably it's also amplifying other things, right? Like segregation of communities, for instance.
Yeah.
So like the whole echo chamber, filter bubble type thing.
Exactly. So another thing that this amplifies is in other applications, if you want to diffuse information and you manage to segregate the network much more, you get stuck within one community, which would be an echo chamber issue or an information diffusion issue as well. Yeah. And there's a bit of a subtle effect of homophily here, which is that, well, it really matters how whether the two groups are heterogeneously connected with more with each other than across or not, because when you have everyone has the same rate of homophily, to say so, the same probability of connecting within and across, you get this effect. But when the minority actually is more connected within themselves than with others, you get to reverse this effect in certain conditions. And you get that a minority can actually overcome their, social capital deficiency, to say so, and the same with recommendations, and actually get more connections. This has also been observed by a recent study, but in a different case. Okafor in 2022 showed that a more homophilic minority in terms of demographics can get better job referrals if they connect more within each other than across. Great. So after this, there's other applications, and I want to relate a little bit to the other problems that we mentioned in graph problems, that of ranking, for example. Espino and Nova in 2022 showed also that the role of homophily and heterophily is quite a subtle one. If you think about the ranking of minorities in the search algorithms, they looked at PageRank, for example, and what they see is that, well, you can measure inequality again at the number of minorities among in top K, or where K is the rank that you get, or by looking on averages. For example, they look at like a Gini index of the ranking score that you might get. Yeah.
Sorry, could you ask for a bit more context? I'm a bit lost.
Yes.
In this particular setup, what is the ranking that we're talking about? Who was being ranked for what?
Oh, in this case, you think about a network in which you're ranking nodes based on the PageRank algorithm. So it would mean the ranking means how you show up in a search result based on your centrality in the network.
But was this is a theoretical result with simulations?
This was a simulated result based on the sorry, I should have mentioned that based on the PageRank equation.
Okay.
And then you see, given a network, you can see what the PageRank score would have been.
Okay, thank you.
A page rank of people.
Sorry?
But it's a page rank of people.
It's a PageRank of, yeah, I mean, they can be people or web pages that are part of different communities. It doesn't, yeah. In this case, they're just two groups with connection. Yeah. The other study, the empirical one, showed PageRank on like real people actually deploying it. This one says, let's take this model with two different communities, preferential attachment and homophily, and see what PageRank would do on it at the numerical level. And they show that, well, this model explains a lot of what we saw in the empirical study, to say that, well, we get conditions in which a minority group gets downgraded or gets pushed down in the ranking, and by how much do they get pushed down in the ranking. But the more interesting part is to say that, well, it really matters how the minority connects with each other, because when you have a more homophilic minority, they can actually be better represented in PageRank as well. So what they see here in blue, green, and red is whether the minority is represented, overrepresented, equally represented, or underrepresented in the search results, if you look at a particular cutoff. And the X and the Y axis is the homophily parameter for the minority versus majority. So what they mean is that a very homophilic majority kind of downgrades minorities. If they're kind of so-and-so, minority is probably going to be fine. And if they're less homophilic, and the minority can be however homophilic they want, but that means they actually get overrepresented in the search results as well. And our current work was trying to prove this theoretically as well. So it's a current project in which we're trying to show basically to prove the distribution of PageRank for models that are based on preferential attachment with different communities, to show this case as well. Okay. Where are we? Great. Are there any questions so far?
So basically, like if you're in a segregated but highly connected community, your eigenvector centrality can still be large.
Yeah, but
Statement.
yeah, exactly. I mean, if you're completely segregated, then it's as if you have two different networks. So if you're two completely segregated groups, your degree distribution is actually the same. Your power law is the same because you're completely segregated. You have two groups. But the moment
according to this model of it.
according to this one. Yeah, but the moment you start to have even a few connections, you're basically competing for the attention of new nodes that come in. as the network evolves.
How should I think about the role of correlated covariates here? So say, I was thinking for the co-authorship network, say the distribution changes with age, and like older researchers have already published more, something like that.
Yeah.
It seems that this would all still go through, it's basically correlated to group identity. Was there anything interesting to be said about the difference between having a correlated or a group variable?
Yeah, I think that would be interesting. I don't think they've done that looking at age as well, but I think it correlates, and we can think more about the, like, pipeline of, we have older researchers who come from more established groups or regions. And one study that I have seen related to that was on PageRank, in which your time in the network really gives you a positive bias to get a higher centrality. So even if a much later node comes in the network, they're quite central, and then they have a lot of like the same number of connections or friends of friends as you do, but they're a much older node. That actually places the new node as a very high disadvantage compared to the old node. So that's one.
I think it would be interesting, because I'm not saying that because I think it wouldn't be a problem if it just turned out to be age, but just because it could have an impact that is much harder to correct for if it's due to some things that are that is more legacy. So I think it could be interesting.
Definitely. I think that would be interesting too.
How much do we know about how actual network recommendation algorithms on these social media platforms?
Yeah.
Do they use things like PageRank or?
Yeah, so for recommendation, they don't really use PageRank, but they do use versions of Friends of Friends or Atomic Adar. Like there's several studies showing that the Atomic Adar index is one that's like heavily used. Some versions of Friends are used. I mean, we don't know exact implementations, but we know that the like skeleton of what structures they use of that. Yeah. Yes.
On that realm, there's, I don't know on social networks, but like on recommendations like YouTube, Spotify, Amazon, like the literature is quite open in a way. So there's I happen to be working on Amazon recommendation systems, and like we published everything, and like we saw the while others were publishing. So like it was actually quite public, and like there's a lot of black boxes, but also there's a lot of care about this kind of issues. So like it's quite open and it's quite public what they're doing.
Yeah, I think that would be really interesting to see what happens with like content recommendations, in which, as you said, maybe we know a little bit more. And yeah, there's a bit of, I think that there's some challenges that I've seen in this work, which think about like, well, I don't really know if I would have formed that connection unless the algorithm would have suggested to me or not. But maybe if I make that connection, that's a good indication that I would have formed it anyway, because otherwise I wouldn't have taken it. So there's some sense of like, how do we, yeah, I guess it's again like this question of like, how much do I create connections that would have formed anyway, or do I like actually push people into a new direction?
At least the platforms would probably know with some experimentation around there.
I'm sure. Yeah. Okay. Yes.
So what about the role of acceptance recommendation? So the way I think about the social networks, not only you get recommended, at some point you send an invitation, the other person needs to accept it or not.
Yeah.
How we might expect like some heterogeneity, especially cross groups. Is there any way like to factor that into this analysis? So because so for instance, if women are more reluctant to accept male friends, then completely fair system might not even be enough to ensure this.
Totally. I think that's a very, very good and big question. I think we need an experiment to kind of see that, and I don't really know of those. That would be great to have that. Yeah, we can model it as different, but it's more out of our own assumptions than what we simulate. But there's a lot of anecdotal evidence for exactly what you mentioned that I've seen, and I'd be curious to see more experiments on that too.
I think there's an experiment that is kind of on Twitter trying to get at the identity of PhD students kind of clicking on following different people and the likelihood of being followed back, and how that changes depending on gender and race. And so I think that may be kind of
oh, that would be great to see. Yeah, that would be cool. And then something about this data set, this data set from Instagram was collected out of public accounts, which are already about a selection bias in the sense of what accounts are more or less likely to accept new connections or so on, because the private ones are already focused on, this is my private connections. I don't want to connect with others maybe as much. Yeah. Good. So, we're at 5. Okay. I don't have much more from here on, but the main point that I wanted to end on this part of the talk is that, well, the knowledge of the network really helps you to know what the impact is on different groups. I'm going to talk about on the next talk on what that means in terms of other applications and how we can intervene in case of like information diffusion campaigns or in opinion aggregation mechanisms. And the main point is that if you don't really know the network, you may think you're doing fine, but you can't really like measure the impact on different groups as much than if you do know the network. And of course, the model that I showed you is like one example of a model. It's simple, it's helpful. Maybe there's other models that we can think about that capture other properties that we care about, but it's a good explanation for the mechanisms that we see, because it contains all the necessary and sufficient ingredients to see some of the empirical results we noticed.
But in some sense, if you know the network structure, then you don't really need to have a model for it, but you could just take the network structure and simulate what the recommendation do.
Well, if I know the network structure at a particular time step, but I don't really know how it evolves. So I would need the network structure at the many evolution points to kind of get a sense of what will happen in the future and what the impact will be. Yeah, which is even harder outside of a company. Yeah. And then the second part, I wanted to mention a little bit about the problem of network interference. It's a topic I'm currently interested in, and I think there's a lot of interesting open directions here. A lot of the algorithms that we use, we don't just like deploy them. We test them out and then we deploy it. Or we test them out, we see how they impact different people. Do they work? Do they not work? And for that, we need something that looks like randomized controlled trials to see to be able to assess whether they work or not. That's not only in the case of algorithms, it's in the case of many kind of network experiments that think about, what is the efficacy of a new drug or a new vaccine, how do policymakers understand the impact of social welfare programs, or in our case, in the case of social media companies evaluating the impact of different recommendations, algorithms on user engagement. Did you continue to be on the platform? Did you accept the connection? Did you talk to your connection? And so on. And in this case, I mean, the setup, we've just seen it before in terms of like causal inference, where like maybe you have a central decision maker like your platform that's trying to deploy a new algorithm, and they're trying to figure out like, well, if I show you some type of connections, or if the feed looks like this, are you more likely to connect with people or to engage or not? And the problem here is that, well, you get the setup is, we've seen in many cases as a potential outcome models that people are setting up with a treatment, some hopefully known confounders and some outcome. And we're trying to estimate the treatment effect of your, let's say, are you shown a particular recommendation? How does that look like, or so on? In the classic non-network mode, you have this assumption that your treatment only affects you. And that's the really big assumption we have in many cases. But that can lead to a particular, giving an example of an outcome model with the treatment effect. In the network interference issue is that you don't have this assumption anymore. Because if I show you a particular recommendation, or I tell you about the feature of the network or of the platform, maybe you go and tell your friends, and that means that, well, that becomes really difficult to measure, because now I don't really know who I show the treatment or not, and that's the problem of network interference. Sorry, I wanted to go the other way around because okay, perfect. So the issue with that is that now I don't have that anymore. Even if, for example, Cortez Rodriguez and many others before them, but I'm giving an example of them defining a potential outcome model that involves the treatment effect of, let's say, your friends, and I is just in your neighborhood for a subject I. Even if I can define this potential outcome model, and I can define then an estimator that maybe is similar to what I've had before, the problem is that as common estimators will have a terribly large variance as high as the maximal degree of the network. So the error will also be really, really high, even though I can design in a way estimators that are unbiased. For example, something that looks like a Horvitz-Thompson estimator. will be mostly unbiased, but then will have absolutely terrible variance because of these network structures.
So why is that? Because treating this one node has a large effect, essentially, or
because you're aggregating if you're saying that my effect is if my effect is affected by all the neighbors that I have, then basically in the variance it goes like the maximum number of neighbors that one node can have. So it gets amplified by that.
But that's kind of assuming if I have 20 friends, then I'm somehow double the impact relative to if I have 10 friends. I mean, I could think about models where it's just the average of my neighbors that matters and things like that.
There are models that think about how much your neighbor influence matters. In this case, I think they take it independently. But if you say like, oh, maybe the average of my friends matter, or maybe it matters to some degree, not to the full extent of, let's say, where's my outcome of this, then you can reduce that variance. So my next point is that it matters what assumptions you make on how your neighbors affect you. But I hope I will answer your question, and if not, let's come back to it. Where are we? Here. I wanted to get to this, which is a good classification of what directions can we go into with our assumptions to reduce the variance of these estimators and to figure out these network interference problems. And one set of directions is the x-axis, which is assumptions on the network structures. If we just say we have disconnected communities and the effect only occurs within my community and I don't talk to people in other communities, if I have sufficiently enough communities, then I can efficiently bound my estimator too. If I have a k-restricted growth of communities, again, I can do a relatively fine job of bounding my estimator.
Sorry, all of these were randomizing treatment at the node level.
Yeah.
And
so,
we can decide on the experimental design, or
they a lot of these try a couple of experimental designs, like for example, like a complete randomized design or Bernoulli trials. This paper tried Bernoulli trials, and I'm not aware of others.
I mean, in principle, you can do more sophisticated things there to reduce the variance.
Totally. I think this paper tried a bunch of experimental designs to reduce the variance as well. And then the other way to do it is to think of like, well, how much do my neighbors actually affect me? Do they affect me a lot or not? And then depending on the kind of assumptions you make, for example, maybe it's just the number of neighbors that affect me, but maybe they don't aggregate together in a way that amplifies the treatment, or maybe I have a lower number of interactions in my actual neighbors. So maybe if I get affected by at least by 3 people, it's as if I'm affected by 6 people or something like that. I have some restricted growth of aggregation of treatment, and I can also do a pretty good job at reducing my variance. So I can make different assumptions on how my neighbors are affecting me, and that's also one direction in which I can help with this.
So just reminding me what the estimate is. The estimate is like the treatment effect of treating everyone versus no one.
Yeah,
or
everyone versus no one, exactly.
Which is one of many things you could be interested in.
Yeah, I mean, this paper, what is it? This paper does total treatment effect, everyone versus no one. A bunch of others do average treatment effect, or you can do like a bunch of designs. But I think the similar analysis occurs. Yeah.
I mean, there's things like I care only about the direct treatment effect, or I only care about the spillover effect. So all kinds of variations of that.
Definitely. Yeah. And there's a bunch of other studies on that too. Yeah. But does this answer your earlier question in terms of how your neighbors affect you? Here, sorry, this.
I'm not sure, to be honest. Because if what I care about is how everybody affects me, and at least if they're not long distance effects in the network, then in some sense, if you can do like an experimental design that's locally clustered treatment assignment, then essentially as the network size grows, it should basically have estimators growing.
That's basically this. Yeah. That's
right,
what it.
But that's not basically fully disconnected some communities, right? It's just if effects don't propagate over longer distances.
Okay. But I think all of these, from my knowledge, they assume that your effects do not propagate beyond your neighbors. If they do propagate beyond their neighbors, I don't know.
Right, but then it seems like maybe related to how the experimental designs are defined. Because if I can locally cluster, then it's effectively
Yeah.
Like have as many observations as local clusters, more or less.
Yeah. I agree. So that's one way in which it feels limited by the experimental design. I think there's maybe a lot of open directions to think about this when you don't necessarily can cluster or when you do cluster the network, but it's not a natural clustering. You just force ego nets around people and then you assume that that's disjoint in some weird version. And I think there's a lot of open directions to think about, like higher level order interactions and what we can do with these as well. Okay, are we, I think we're close to time, but
As per ICA's rule, we can go until 5:30.
okay, well, this is where I wanted to end and see if there's other questions. There's a lot of open directions I wanted to see. Generalizing beyond parametric models that I've mentioned before, there's a lot of new and interesting work there, but the models that I mentioned are, interesting. They're also limited by the parametric models that we enforce on them. So, what kind of network properties cause this kind of bias to be projected on different embeddings that we use in algorithms. There's a sense of that in PageRank, uses basically an embedding of the network in which you do random walks on your network, and then that creates some bias. But what exactly makes that embedding to be more biased or less biased in PageRank? That's an open question at least a theoretical level. There's a lot of questions regarding bridging causality and fairness and understanding the causal connection between algorithms and bias. These network models is one way to think about the evolution of a network in the absence of an algorithm and comparing it, but there are a lot of open questions regarding that as well. And of course, there's this question of this feedback loops and long-term effects of what happens at the long term. And a lot of these analysis on network models think about the asymptotics of the network and what happens on the long term, but how do feedback loops throughout the network may get amplified? That's also what a lot of people are doing. It would be interesting to see. And of course, one other direction that's interesting is to think about when do people kind of strategize for making connections, when they have an incentive to make a new connection or not. An interesting property of the model that I mentioned before is the same authors show that if you're trying to maximize your degree, this model is the unique universal Nash equilibrium among a set of different strategies that you can have for modeling the network. So that's one interesting direction as well. And we can think about these different objectives that we've been talking about. Maybe you're optimizing for user engagement, but you see some bias at the level of what do people how do people connect to each other? And if you see that one group connects less, is that actually bad? Is that just bad in terms of the objective you're optimizing, or is it actually can we find a better way to define the objective to begin with? And there's a lot of interdisciplinary studies that I think we can draw from both econ, sociological and empirical studies, and things beyond network models that would give us a lot of tools for this. So yeah, and I think mechanism design is a big part of that. We with some colleagues, we thought a lot about how to bridge machine learning and mechanism design to think about fairness definitions, where are some gaps, how do we model things in a way that's capturing issues between different groups or at the individual level. And I would love to talk to you more about this or any other questions you may have. So thank you.
Well, thank you.
Thank you.
And we'll continue tomorrow morning. And for the speakers, we have dinner, we have meeting there at 6:40. So let's meet in the yard.
In the yard, Anna. Yeah. The yard, and that too.
Oh, I see.
But,
Okay.
yeah.
No,
How long is it? How long a walk is it from Lumberton?
55 minutes.
But
Oh yeah, I like this.
We want to be, yes, 6:20,
Oh yeah.
and then
Should we already there, or or we
But-
don't know that?
I'm gonna.